I'm going to put information in front of it. I'm going to put it in this box. Now, because I put it in this box, can I see this data anymore? Nope. It's in the box. I'm going to label this layer 4 information. Now, on top of this layer 4, I'm going to have layer 3, which means I'm going to encapsulate this box with another box, which means I will not be able to see the layer 4 box because it's inside this box. And now here's my layer 3 information, which means now I'm going to even encapsulate it again with layer 2 information. I won't be able to see this box because it's in the layer 2 information. If I said, and let's look at this, I got my layer 4 information, I got my layer 3 information, and I got my layer 2 information. As a CCNA, and a lot of CCNPs will answer this question in this manner. When I ask the question, okay, when I strip back a layer 3 header, or if I remove a layer 3 header, what will I see? And you know what they all say? Most of them, I will see the layer 2 information. No, you won't. Guys, in order for you to see the layer 3 information, you have already stripped back the layer 2 information. The layer 2 has encapsulated the layer 3. And this is what we mean by encapsulation. We have to understand that this TCP header is just for layer 4, which means in my layer 4 information, I'm going to have the source port, the destination port, the sequence number, the acknowledgement number, the window size, which we're going to be talking here shortly. All this information the data gets encapsulated with all this information. And then all this information gets encapsulated with layer 3. It's 20 bytes in size. Well, what does that mean to us? 20 bytes? Well, remember my scale that I was telling you about bits? Let's do it again. A bit is 1 or 0. 4 bits of the nimble, no need to write that. 1,000 bits is a kilobit, but that's not how far we want to go. How about 8 bits? 8 bits equals 1 byte. So if I have 20 bytes, how many bits do I have? What's 8 times 20? 160 bits. So what do we see when we go look at a UDP header? Man, that is beautiful. Source port, destination port. Almost 3 times less the size of a TCP header. Only 8 bytes. Why would we want to use TCP and UDP communication? Well, we want TCP for guaranteed delivery. When do we not want guaranteed delivery? Well, if we want something fast, speedy, and we're not really worrying about it, what if we're sending out data? What if PC1 is sending out data to PC2 every second? Or how about 4 times a second? Do we need that guaranteed every time? Nah, not at all. Not at all. Now, we could have the application on PC2 saying, look, if I don't get information after 3 seconds, then, I don't know what to do. At that point, you can shut down the application, send a warning message, and say, hey, we don't have any communication. I mean, that would be the wise thing to do on PC's 2 end. Well, both of them, because they might need to be communicating back and forth. But at the same time, if this is just a server, if PC1 is just a server sitting over here, and he's just feeding out information, we can actually mix TCP and UDP. I can actually use a TCP method to establish the connection originally, and just from there, just stop it. At that, we're only sending UDP traffic. That's definitely possible. Because we don't want to guarantee 4 times a second that this traffic went across. Not at all. All we want to do is just send the data out fast as possible. What can you think that might want to do that? I mean, stock information, that could be one. Think about you designing a network for a stock exchange where the data needs to be guaranteed, it needs to get there quick, fast, but not necessarily 100% reliable. Why would you want TCP traffic to be 100% reliable? I mean, web browsing, wouldn't you? Would you like to get everything guaranteed onto your web page, or you just like to, get whatever might come? Now, again, guys, what does this really mean? Does it mean the stock exchange data isn't guaranteed? No, I don't know. I'm not on the stock exchange network. I don't work on it. And if it was, some data probably would be and some probably wouldn't. But it all depends on the designer of the application and what these people want to do. You have an option. Your option will be UDP or TCP. Pick an option, whatever you want to happen. I know for a fact, if I'm doing banking information, don't you think that I will want to do TCP? I mean, you got to admit, if I swipe my card here at, let's see, Kmart, that information comes over here to a server. And where do you think this is handling the process? Here, you swipe your card, comes over to this server, which is probably sitting at a data center somewhere. But where do you think it's going? It's going to some bank over here. Whoever holds the credit card. So don't you think we'd like to have guaranteed information? I bet you the banks want to, because they want to make sure to get their money. They don't want you. We don't want no claims of spending a bunch of time trying to figure out if this card was charged or not. They want guaranteed. So our next topic is windowing. Windowing is an interesting concept. Although this graph might not be 100% accurate, we're not looking for accuracy 100% of the time. We're looking for, can you understand the concept? So I want you to think about windowing as a way of me finding out that perfect speed. So here you go. You got this ledge sitting here. You got your window sitting here. And right now the window's closed. So what you do is you open up the window a little bit. And here we go. Here's the window. All right, and you got all these dots on the screen. And air rushes through. Now, eventually, you're still hot. You open up the window to get a little cool. So what do? Let's open the window a little bit more. This allows more air to come through the screen or come through the window and be able to give you cool, and maybe you cool off. Now, what happens if you get a little bit too hot? You get to close this window and lower the flow of air. And that's the concept of windowing. Let's see how this works. I'm going to send one piece of data. And I'm going to send this data from this PC over to this PC. Now remember, windowing is in our TCP. So remember, this is going to be happening via our TCP communication, not our UDP. And I'm going to send this piece of data over. Nice. Now, if I sent this data like this, just like this, the whole time, this might take me 1 week to transfer that data. Now, I get an acknowledgement back stating that I got the data because this is TCP. And then I'm going to send this data again, but I'm going to send it this much data. Ooh, that's nice. I sent this much data. It comes through. Now, at this speed, it might take me 5 hours. to download. I get an acknowledgement back, and then I'm going to try to send this much data. Now, at this speed, it might take me 15 minutes to download this file. I get an acknowledgement from this one, we're good to go. Now I get this, I send this much data. This might take me 5 minutes to get my data, to transfer the whole information I need to transfer over. But wait a minute, I don't get an acknowledgement back. Now if I'm not getting an acknowledgement back for all these pieces of data, we got problems. That means somehow this PC2, did not get that data. Now it's time to back off. This is us opening our window every time until the window gets so wide open that we start to lose data. When we start to lose data, we close the window. We shorten it a little bit more, saying, sorry, too much air is coming through. Let's shut it down just a little bit. And then we get this steady stream of 10 minutes. Have you ever seen data doing this as soon as you download something? 1 week might be an exaggeration, but he might come out and say, this is going to take 7 hours. Then it drops down to 3 hours. Then it drops down to 1.5 hours. Then it drops down to 50 minutes, 25 minutes, and 17 minutes. And then eventually we get this, then we might even drop down to 3 minutes and then probably come back up to our average of 10 minutes. And then it will stay here at 10 minutes throughout the rest of the duration. And this happens quickly. Haven't you noticed this before? This is windowing doing this job. TCP is hungry, which means if you have problems with your bandwidth getting eaten up, and your solution is, let's double our bandwidth. And then you double your bandwidth, and then you say, man, that's getting used up too. Well, let's double it up again. Well, if you're using TCP applications with this windowing will keep going until it can't go anymore. And because of that, you have a potential of eating up no matter what bandwidth you put on there. And maybe quality of service is a better method. We send data out. The acknowledgement that we're getting back is obviously the acknowledgements packets, or not the acknowledgements that we're getting back from TCP, not the three-way handshake, which we're going to talk about here in a minute. Because you saw in the TCP header, we have the three-way handshake, and then we have the TCP header that we were looking at. And in that TCP header, what did we see? We saw secret numbers and acknowledgement numbers. This has nothing to do with the three-way handshake. The three-way handshake has the SYN and the SYN ACT and the ACT. These are messages. So the SYN message is a synchronization message, and the ACT message is an acknowledgement message. These are acknowledgement numbers and sequence numbers. Two different things. Let's talk about our sequence numbers. Sequence numbers is an interesting concept because secret numbers guarantee each data, each packet that's being sent out from PC1 going to PC2. It has this method of understanding how the data, this method of guarantee that the data is coming from PC1 to PC2 by using this method that we call sequence numbers. And let's find out why. PC1 sends out its first packet. Now this is after the TCP session has been established, and now we're starting to send data. And we're sending it via TCP, which means here's my data and what's going to be on top of that data. Guess what? You guessed it. My TCP header. You guessed it. Which is really layer 4, right? It's my layer 4 information. So in this TCP header, we're going to have secret numbers and acknowledgement numbers. Now I'm going to send out a sequence number of 100. Now here's the interesting thing. When this data comes all the way over here to PC2, PC2 is going to say, I got a piece of data with a sequence of 100. Now, PC2 is going to look at that and say, all right, I'm going to acknowledge your 100 by sending you an acknowledgement of 101. Now, this is weird because you figured it would send back an acknowledgement of 100, but that's not the case. When PC2 sends an acknowledgement of 101, he's saying, hey, this is the next packet, the next sequence number that I myself am expecting to see. That's what that means. It's a little weird, but that's exactly what that means. So now with this acknowledgement, don't pay attention to these sequence numbers on this side at this moment. We're not worrying about that right now. So at that moment, or these acknowledged numbers here, we're only worrying about the sequence numbers on this end and acknowledged numbers on this end. So here, I'm going to send an acknowledgement of 101. Because PC1 gets an acknowledgement of 101, he says, okay, PC2 must have gotten 100 because he's expecting to see 101. So I'm going to go ahead and send that. Now remember, behind here is data. As I'm sending this, they're not just sequence numbers. Guess what? It's data behind there with the sequence number on it. So I'm going to send my next piece of data with a sequence number of 101. That comes over here to PC2. PC2 says, okay, I got a sequence number of 101. I'm going to send you an acknowledgement of 102. Okay, that comes back over to here. PC1 says, oh, I'm getting an acknowledgement of 102, meaning that PC2 must have gotten my data with sequence number 101 because he's expecting now to see acknowledgement 102. So now I'm going to send my next piece of data with a sequence number of 102. That comes over here to PC2. PC2 says, I'm getting a sequence number of 102. I'm going to send an acknowledgement of 103 because that's what I'm expecting to see next. That comes over to here. PC1 says, I'm getting an acknowledgement of 103. That means PC2 has received the sequence number of 102, since I'm getting a sequence number of an acknowledgement of 103. So now I know the next sequence number I'm going to send out, and the next piece of data is going to be 103. Now, the reason why you see the sequence number here and the acknowledgement on both sides